Hello, Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. The question that I was asked during one of the live streams was asked me to explain polarization. Now, we hear this word in ham radio a lot, and the principles that apply to polarization, like in a camera filter, apply just as much to ham radio. Because we're dealing with electromagnetic waves and they all behave essentially the same with polarization. When we talk about polarization, we're talking about an electromagnetic field. The electromagnetic field has an electric component and an magnetic component. Okay, the ratio between the two in terms of peak value is the impedance of whatever medium it's in. For example, in air, it's about 377 ohms, meaning the electric field in voltage, volts per meter actually, is 377 times what the magnetic field is. An electromagnetic field consists of an electric field and a magnetic field at right angles to this one. So if it's a plane wave, you'll have the physicality to the direction of the light going down this way, and the same 90 degrees for the magnetic field. The electric field is measured in volts per meter. The magnetic field, interestingly, is measured in amps per meter. Now, if you divide the two to get the ratio, the per meter part cancels out, and you get volts over current, volts over amps, which of course we know as the impedance or the resistance. We use impedance when we're talking in electromagnetic terms because in impedance there's often a phase angle that we need to take into account. Now here's something that's very important. The reference for any twist, skew, whatever, the reference from which you measure that is the electric field. Okay, the electric field. So the electric field is measured as 0 degrees, and whatever the current field, the magnetic field is doing, will be 90 degrees off from that. So polarization. For most hams, we think of horizontal polarization for things like dipoles. The electromagnetic wave emitted by a dipole is horizontally polarized because the motion or movement of the field voltage is in the same line as the horizon. Now, if we twist it around and make a vertical, that will also twist the wave around and make it vertical. And again, the electrical one, which would lay the magnetic field down in parallel to the ground. Now, horizontal and vertical would seem to cover it. Every antenna that hams use, whether it be a dipole, a Yagi, whatever, a beam of some kind, hex beam, whatever, have an obvious polarization. You just look at which way the E field or electric field goes, and that is, by definition, the polarization. Now, polarization can become iffy if you do a full wavelength loop, vertical. So you hold the tops up with trees and the bottom down just with ropes to keep the square or the triangle in shape. Depending on where you feed it, you can make it either vertically polarized or horizontally polarized. What stands to reason that if you feed it halfway in the middle, you'll get a cockeyed rotation, but still a planar rotation, okay? Now, a funny thing happens when your waves hit the ionosphere. They're split into two parts. They become, instead of a plane wave, they now become circularly polarized. There is the ordinary wave, which is most of the energy, and the extraordinary wave, or X, which is 90 degrees out of phase, but it's also, both are circularly polarized. One is circularly polarized one way, and one is circularly polarized the other. Now, this leads to the question of, can you create an antenna where you can force the output of the antenna to be circularly polarized? And you certainly can. I'll show you how. And would that help in receiving a circularly polarized signal? Well, it would either strengthen it 3 dB above, which you'd get with a linearly polarized antenna intersecting with a circularly polarized wave, or you would get much less, because if the polarization is the wrong way, you won't be able to hear it. Okay, it will help to look at some pictures. This picture comes from the ARRL handbook and shows a horizontally polarized electric field. Note that Z is vertical, Y is horizontal. And this wave is a plane wave. It's always in the same plane, and it is horizontally polarized. Now, up 90 degrees away from it, the H field, more often in textbooks called the B field, is the magnetic field. Okay, so electric, magnetic, they go together. The ratio of the two is the impedance of the medium that they're traveling through. Now, can we make this a little more clear? Sure. Let's take a look at this thing here. Note that in this illustration here, we have this part called lambda right there, going up and down, showing that the peaks are 1 lambda or wavelength apart. Now, as the red electric field comes out at you, you can see it. It's always plane, but it's vertical plane. Okay, and the magnetic field, if you come an additional 90 degrees over, you get the magnetic wave. Now, let's do something strange. What would happen? Is it possible to create a circularly polarized wave? Well, indeed, we do that. This is what comes back from the ionosphere. Now, look, it's hard to do. If I did this, I would have used different colors. Here's your axes right here, up and horizontal. Now, notice this spinning arrow right here. Okay, that spinning arrow, which should be a different color, otherwise it's very hard to pick out, is going around in a circle, tracing out what looks like a spring or a helix. Okay? And what this is doing is constantly changing the polarization of the wave, but there is a particular way to do this. A complete wave, taking you back around to the beginning, is 1 wavelength. So artificially spinning an antenna is not going to do the job. To create true circular polarization, it needs to do 1 complete loop. 1 complete loop in a wavelength. This is really important. Now, something else I want you to notice. I want you to notice there that in that wave, if you point your thumb in the direction of travel, and the wave is turning this way, okay, this is called right-hand circular polarization. If your thumb is pointing in the direction of the wave travel, and the rotation is in the other direction, it's left-hand circular polarization. So you see there's no loss of momentum if you have a plane wave hit the ionosphere and it splits so that part of it is right-hand circular polarized and part is left-hand circular polarized. So if we look here in the diagram, we see that this is, because it's coming around this way toward us here, you put your thumb in the direction of travel and your fingers in the direction that the wave is rotating, and this is a right-hand circularly polarized wave. You can flip it over and do the other if you want. So you've got a choice. Now, this is, if you wanted to create an antenna that could create circular polarization going out and coming in. Now this shows it for a Yagi, but let's just look right here at these two elements right here. Lay them down on their sides, lay them down on their backs. So you got one wire strung east-west and another wire strung north-south. You got a little relay box in here, a little T-junction. Okay, some lines, they give you some actual practical lines here. This right here is a quarter wavelength. Okay, so if the relay is in the closed position, shown here, the signal goes here, goes up a quarter wavelength to here. And it goes a quarter wavelength here and another quarter wavelength to the other antenna. So one goes to the east-west and the other goes to the north-south. This will create one type of polarization just with those two crossed antennas. Now if you flip the relay over to here, now you've got a quarter to go here and a quarter and a quarter here, that's half. So you're 90 degrees out of phase with each other, and now this antenna becomes circularly polarized in the other direction. So you could build an antenna like this. And if you're listening to a station and you flip the switch and the station fades, you know you've got the right polarization. If you flip the switch and the signal gets stronger, you've got the correct polarization for that too. This will work at HF. It will also work this way with satellites. Okay, so let's talk a little bit about this. So when you're talking to satellites, amateur satellites usually have a single polarization, linear polarization, okay? But the problem is that the satellite's constantly turning, okay? So if you send up with circular polarization in the right way, that antenna can pick it up. Now, we'll cut it by 3 dB, but at least it'll pick it up. If you go the other way, you do the other thing too. So you will see some satellite antennas that look like they have a helix coming out of them. That helix is used as a director to circularly polarize the waveform in the direction that you want. Now, can you make a helix antenna at HF? Yes, but it would be enormous. Absolutely enormous. So that's why we just do the trick with the 90-degree out-of-phase cross dipoles in order to create and receive circular polarization. Now, there is one other kind of polarization I want to talk about that you almost never hear of in amateur radio. You take your cross dipoles straight up, you've got a nice circular polarization. But if you tip it over at an angle, you're over here trying to listen to this. What is going to happen is you get, are you ready for this? Elliptical polarization, where it changes values and so on constantly between the electric and the magnetic field. Circular polarization is a special case of elliptical polarization, which is the more general form. Okay, so we've talked about every type of polarization. This is why, when receiving something that has bounced off the ionosphere, like something across the country or something like that, it's coming at you circularly polarized. Your antenna, whether horizontal, vertical, or cattywampus, takes the component of that circular wave that's in line with it, which means you get half of the signal, because the other half of the signal we're not listening to. Obviously, it cuts off as the cosine of the angle away from this thing. But the point being that you can use either a horizontal dipole or a vertically oriented antenna to receive signals that come from the ionosphere And the antenna will not care what the polarization is because it's just sort of picking out a linear component of that signal. So you can do it either way. If you want to get really fun with it, go do the cross dipoles with the relay experiment. And what you will find with that is some stations will get stronger when you switch to right-hand vertical polarization, and others will get stronger when you switch to left-hand polarization. Now let me tell you about something. If you're going to transmit back, and you remember it's the bit with the thumb, well, if you're going to turn the thumb the other way, the fingers go the other way too. So if you had circular polarization coming in, you're going to have to reply. Well, you can reply with circular polarization in the opposite sense. So if it comes in right hand, it's got to leave you left hand. Okay, I know that's a lot, but people who are into satellites know about how this kind of thing works. And it's really very cool. Now, when I talk about polarization, is this the same as a polarizing filter in photography? You bet it is. Same thing, same concept, same type of stuff going on. If you send it through a filter that receives vertically polarized, and you put across it a filter that receives horizontally polarized, you won't get anything through. But if you slide them so that they're in line with each other, you get the maximum amount. These are used for neutral density filters for certain types of camera activity. You can actually vary the amount of light from almost none to full with these. And same kind of thing you can do with electronics. So there you have it. That's a little bit of a long-winded account about polarization. But I just wanted to show you some of the terminology, some of how it works, a practical way to build an HF circularly polarized antenna, and talk a little bit about circular and elliptical polarization. I hope you found that fun. And if you did, you might want to go back and listen again. There's a lot to it. So there you have it. We've talked about a lot of things. If you found this video to be helpful, please subscribe. I've got plenty of videos like it. Also, click the bell so you'll get notification. Also, if you would like to help with the financial expenses of this channel, go to dcasler.com/support. There's several different ways that you can do it there. A one-time subscription or Patreon. I kind of like the Patreon because they keep track of you there, which the subscription on Google does not do so much. There you have it. Until we next meet, 73.